All right, everybody, come on in. Come on in, settle down. So, welcome back. Welcome to February. I want to apologize in advance. I'm a little bit under the weather, so we'll see whether I can actually get all the way through a lecture or not. It will be interesting to try. So, if you remember from last time, settle down, everybody. If you remember from last time, we talked about a couple of things, among them control over processes. We talked about fork, wait, and optional exec. So if you remember here, the pattern was essentially that you fork, and at the moment that you fork, all of a sudden there's two absolutely duplicate processes that come into existence, and this procedure called fork returns in both of them, but with a different value depending on which one it returns in. So that's a little bit of a thing to wrap your head around the first time. If it turns out that what comes back from fork is something bigger than 0, then it's the parent process, and you get to find out what the PID is of your child. On the other hand, if what comes back is 0, then you are the child. Okay, and then of course the other option is an error, which we hope doesn't happen too often. So the other thing I'm showing here is a typical pattern is that the parent will then wait for the child to finish, and this integer variable that you're passing a pointer in to wait basically is given the return value from the child, and that's the exit value. Notice here's another part of the pattern we talked about, which was that the other part of what we talked about was this notion of execing. And so even though you've forked and made a complete copy in the child, then if you do an exec, what happens is all of the data that you copied gets thrown out, and you start running binary that's at a given place in the file system. So this is kind of all of the things about fork in one slide. Now, there may be many interesting things that come to mind as a result, like why did we bother copying all of memory space if we're going to just throw it out with exec? How many people think that's a good question? Yeah? Well, that's because for historical reasons, that's the way fork worked. Now, usually there's many other ways to use fork, many of which it makes sense to have a full copy of all the state. But anyway, this particular pattern I'm showing you here is something that you might actually find with a shell. Were there any questions on this before I moved on? Now that you had the weekend to cogitate, yes?
Is there a different system call that doesn't replace the current process?
Oh, you mean other than exec?
Yeah.
Well, yeah, you could do anything you want other than exec, and you don't replace the current process.
Okay. Well, like, is there a system call that does the new executable but without replacing the current process?
No, because basically when you're doing an exec, you're basically saying, I want to start from scratch with this new thing that I've pulled out. Yeah. Any other questions? Yeah. So the question is, isn't there a lot of overhead in copying all the memory? That was your question? Yeah, so good. So believe it or not, in the old days, when fork was first came up, they actually did copy everything. However, today what happens is the page tables are just copied. And so you're, like you said, you're actually copying pointers to the pages, not the pages themselves. And we'll talk more about that a little bit later. So it's not as expensive as it seems, but it still seems a little wasteful. Okay? And by the way, I will finish this thought by saying that in Linux, there is a system call that you can use that doesn't necessarily copy everything and is kind of like fork. Yes? What happens if you malloc before fork? If you malloc before you fork, then basically that's part of the memory space that gets completely copied. So the thing that you've malloced, there's a copy of it. You're not sharing. So there's no sharing as a result of the copy. It's literally a completely separate copy. Okay, so whatever fun thing you might want to come up with that you think will give you a way to share back and forth, it doesn't work that way. Yeah. I have no idea. So the question was, if you malloc after a fork, will you get back the same address? Probably, because what you're copying is the user state of malloc, so I bet you would, but I wouldn't want to be held to that. And it's not part of the API, it's not required, and I wouldn't count on it. All right, good. So the other thing we started to talk about is scheduling a bit of how threads are actually made to work. And we talked about internal events are ways for a thread to give up its state or give up its CPU. So one of the options is blocking on I/O. We talked about waiting on a signal for another thread. We haven't really said a lot about that yet, although we did briefly talk about signal last time. And a thread could also execute yield. And this was this idea of maybe you have a compute pi procedure, which in this infinite loop, it's computing the next digit and it's yielding every digit. And as a result, you're sort of giving some other process a chance to run for a little while by yielding. Okay? Now this is a pattern that was absolutely necessary in some of the early personal computing systems that didn't have preemption as a way of giving up the processor. It's also used in a lot of user-level thread libraries where you're giving up the CPU to some of your other friend threads. And we'll talk more about that as we go on, too. Okay, so, and if you remember, the stack for yielding looked like this. Remember, stack rows down. You're busy computing pi. You do a yield operation, which basically switches into the kernel thread, okay, which through a trap to the OS. Okay, it's a type of system call is yield. That goes to the kernel yield portion, which then runs a new thread and does switch. Okay, and that will switch to another thread. And how do we run the new thread? Remember, we have to pick a new one. We switch the registers. We do some housekeeping, and we run the next one. And one of the things, how does the dispatcher switch? Again, save anything the new thread may trash, and maintain isolation between the two. And I kind of showed this example, which I'm sure you've had the weekend to think about, right? Which is we have this procedure A calls B, B goes into an infinite loop and keeps calling yield. And so if we have two threads, S and T, and they've been running for a while, today we're going to talk about how to actually get them started. But let's assume that they've been running long enough that we've got a pattern going here. Then thread S, the stack for thread S looks like this. It's got A, then it's got B on the stack, and then it calls yield. And yield is a system call that calls run new thread and switch. And what does switch do? Switches, saves out all the registers for thread S, loads in the ones for thread T, and then switches the stack pointer. And as a result, returning from switch actually returns up the right column of stacks rather than the left column of stacks. And then, really, we don't go all the way up. What happens is we go up to the while loop. We call yield again. We call run new thread. We call switch. And poof, it switches back, and we run for a while. So this is an example of how, if there are only two threads in the system, S and T, they will keep going back and forth like this as they're going through their while loop. Okay, were there any questions on that? Now remember, yeah. Can you say that again? copying. No. So what's actually happening, I think if I understand your question, this is a good one. So all of what I show you here is stack is in memory. So there's no copying involved. What is copied is in switch, we got to save out the hardware registers. That's copied, not the stack, just the registers. And one of those registers is a pointer to the stack. And so when we do switch, we save out all the registers and we load in the new ones from thread T, part of which is the new stack pointer, which is pointing over here rather than over there. But we're not copying any of the stacks, so none of that stuff is getting copied because it's already in memory. There was a question? No. Okay. Yes?
So, like, I don't know if I missed something, but do you have, like, an actual system, or is it just, like, right now?
There is a way to actually yield, yes. So think of this as an actual system call. Good. Now notice that yield here is a pattern for any number of things you might do to give up the processor, as I mentioned earlier, internal events like I.O. So if you were to actually, if thread S was running along and all of a sudden decided to read from a disk, it would go through this switch process as well, because when you go for a long I.O. operation, you want to switch who's computing on the processor. Okay? Same as yield. Good. So goals for today is I want to finish discussion of threads here. And then we want to start talking about concurrency and the need for synchronization operations. Because once you've got more than one thread running in the system, then all bets are off if you're trying to share any data. Things start getting really messy really quickly. All right? And I don't know, in 61C, I don't think they really talk much about locks anymore, do they? A little, but not much. Okay. Well, we're going to try to fix that. So what happens when a thread blocks on I.O.? Well, say I'm going with the copy file routine, and it's calling read to the disk, and that read is going to execute a system call. So what happens? So the user code invokes the system call. You remember this from last time, right? The read operation's initiated. Okay? It switches into the kernel as part of the system call. Excuse me. And then you're going to do run new thread and switch. So notice that this pattern looks an awful lot like the yield pattern did. Right? I mean, it looks exactly like that. And that's what's kind of cool about this pattern of the way these stacks work is basically you can switch to a new thread as a result of a yield, as a result of an I.O., as a result of, in a moment, I'll show you a timer interrupt. There's lots of ways that you can do this. It's all handled in the same way, which is kind of what makes it clean. All right? And thread communication has a similar property to it. All right? So if you're waiting for a signal join or networking, whatever. Now, the problem, perhaps, with these patterns, which are all internal events, is what happens if a thread goes off into space and never executes an internal event. Okay, it doesn't do yield, it doesn't do any I.O., sitting there spinning in an infinite loop, whatever. Then in the some of the early personal operating systems, like the Macintosh and Windows 3.1, what would happen then is the whole system would lock up. Okay, because one bug in one application running would lock everybody up, and game over. And you have to reboot the system, right? So that seems unfortunate, right? So we would like to have ways to reach out and cause a thread switch preemptively, okay? And so those are external events that come in. So what happens if a thread never does any I.O.? Okay? So what can we do? Well, we utilize external events such as interrupts, okay, signals from hardware or software that stop running code and jump to the kernel. A good example of an interrupt's the timer, okay? And so what happens in all modern preemptive kernels is there is a timer that's going off on a regular basis. That timer then goes into the code that's running and forces a switch. Okay? And if we make sure that these external events happen frequently enough, then everybody gets to go, even if somebody is crashed. Okay, that's kind of our desired goal here. So let me say a little bit about interrupts. I didn't say as much about these couple lectures ago as I would have liked to. So interrupts are literally physical signals coming from devices that tell the CPU to go off and handle it, an interrupt, okay, handle an interrupt handler. And so, for instance, here's a disk. There's a single line from that goes into an interrupt controller. The interrupt controller typically has a mask, so you can turn off these bits if you want to. So you could say, well, I don't want to hear from the disk drive here at all. Or you leave it on. Okay, and then those bits that get through are priority encoded, and that priority encoding is sent to the CPU along with an interrupt signal. So as soon as somebody raises a signal, then the CPU, assuming it's enabled, the CPU says, oh, I better handle an interrupt. And what it'll do is it'll actually save all the state that's currently running, and it'll go off onto an interrupt vector. Okay? And so these are physical signals. Okay? And I like to point this out because I know sometimes it's very easy to take a class like this and sort of forget that there's hardware underneath all of this. Right? This is not just virtual. This is reality. Okay? And that's not to say software is not real. No judgments here. So for instance, the interrupt identity comes in as a number to the CPU. The mask enables and disables. Priority encoder picks the highest one. And there's also some interesting options here, like a software interrupt, which is often used, where something's happening at high priority, and then you set the software interrupt, and you return from interrupt, and it'll when that priority is low enough that the software interrupt can come in, then it'll continue afterwards. So that's a nice feature. The timer is also a device on the interrupt controller or in the chip associated with it that is allowed to interrupt at a regular basis. And the CPU can basically disable all interrupts with an internal flag. Now, we'll talk more about this later, but what I wanted to say is as soon as an interrupt is acknowledged... Oh, yeah, go ahead.
How can software interrupt running different software?
What happens is you set a bit in this controller that says, go ahead and interrupt me. So if you set a bit here, then this comes in as a hardware interrupt, and it'll look just like a device raised an interrupt. But since it's a different one from all the other ones, you can have this one be a lower priority than the other ones. You don't seem to buy that. Yes?
Is interrupt disabled bit used to...
So all interrupts are asynchronous. So what the interrupt disable bit is for is the following. Suppose that the disk drive generates an interrupt. I raise the interrupt line. The CPU, the first thing it does is it turns on the interrupt disable bit as it's acknowledging this. And then the CPU goes in, disables that interrupt line from the interrupt mask, and then turns the interrupt disable back on. So what that does is it gives a little bit of atomicity. We'll be talking a lot more about that over the next couple of lectures. It gives atomicity to the interrupt so that you don't get a situation where you keep getting this interrupt happening over and over and over again and you never have any chance to do anything about it. So because that interrupt line is raised, so as soon as the CPU takes it, you need to disable all interrupts. And so now the CPU can do something without being disturbed by the interrupt. Okay, so that's part of the atomicity. Okay. There's also typically something called a non-maskable interrupt, which can't be disabled, and that's for things like power is failing. Hurry up, do something quick. So an example of a network interrupt might be the following. So here we're running along, some code. The interrupt occurs. That typically causes a pipeline flush in the processor. The program counter is saved. All interrupts are disabled. That's that interrupt disable bit. And we enter kernel mode, and then we run our interrupt handler, and then eventually we return from interrupt, restore the PC, enable all interrupts back to user mode, and continue as if nothing happened. So there's several things I want to point out on this slide. So first of all, what's on the left here is user code, let's say, is running along, and that interrupt inserts itself in here and stuff happens, and then it continues without having to know that that interrupt happened. Okay, so that stuff happens is an important thing to note here, okay? We're able to basically continue as if nothing happened. And the other thing I'll point out is part of this pattern of interrupts is I save everything, I disable all interrupts, and then it's up to the kernel to decide, okay, I'm going to disable the interrupt that I'm dealing with, or I'm going to change the priority of the interrupts, or whatever, and then it'll re-enable interrupts so that if there's something that's a higher priority interrupt, it can now continue, okay, or it can now be registered. So, for instance, it may be that the timer interrupt is higher priority than the network interrupt or something, and so when a network interrupt comes in, I re-enable things so that that timer interrupt could still come on even though I'm servicing the network interrupt. Okay, so that's what's in red here, saving and restoring registers, is about being able to return back to where I'm going, and then changing the interrupt priorities is about allowing other interrupts that are a higher priority to even interrupt this interrupt. Okay, good. So it's a hardware invoke context switch, yes?
So in the case where we're handling an interrupt at a higher priority, skip all the bits of like saving the PC and flushing the pipeline and just after handling that interrupt, we go back to the first interrupt?
So maybe not the way you're thinking, okay? So the question here has to do with how does this interrupt to the interrupt work, right? So I will point out the following. Imagine this code here. We take an interrupt, we go, we raise priority, we re-enable interrupts. At this point, the code that we're running in here is kind of like this code. So as we're running along, if another interrupt happened that was higher priority, we would just pick off over here, do the same thing, come back. So it's exactly the same. It's nothing special. Okay? And you could have several levels of recursion. What that means, of course, is that there's got to be several levels of interrupt stack as well, right? That you have to be able to switch in and out, because otherwise this gets really confused. No question. You had one. Yes?
So do you have to, so you only disable the higher priority interrupts when you're doing the first saving of the interrupts, and then you disable?
So basically, anytime, this pattern, this is the pattern. You always disable everything, adjust things to the new state that you're in. So I know that I'm handling this interrupt. I'm going to disable everything of lower priority. And then you re-enable everything. And that re-enabling everything means basically re-enable those things that I'm allowing to be enabled by the mask.
So you start the interrupt handler with disabling part where you're saving everything.
That's right. This is crucial. Disable all interrupts, because this, what's in red here, you got to be very careful to not be messed up with. Otherwise, you get a mess. Yes. Okay. So now let's go back to what we were talking about. So how do we fix our dispatcher problem where we have some errant routine that refuses to give up the CPU? Well, very simply, we're busy running. An interrupt comes by. It hits the timer interrupt. We run new thread, and we switch. Okay? And so then the timer interrupt basically does some periodic housekeeping and runs a new thread. So basically, this what happens as a result of the interrupt looks exactly like what happens as a result of a yield or what happened as a result of I/O. Okay? So again, it's the same pattern as far as the stacks are concerned. All right? And that's kind of why we're able to basically insert interrupts in here or do yield or I/O, whatever. We can use that to switch who's got the CPU. Okay. Now, I want to point out a little bit about the x86 here, because you're going to be dealing a lot with it, and actually there's a couple of files in Pintos there I'm referencing. But if you look at the hardware spec for the x86, what happens on either a system call or an interrupt, it's basically going from user mode to kernel mode. So that means that the level goes from 3 to 0. We put the flags and the current program counter, that's CS:EIP, into the task segment. We basically, the task state segment, we basically put the stack for the kernel into the stack pointer. So what that means is that as a result of the hardware being asked to do a system call or an interrupt, it automatically saves out some crucial user state and switches in a new stack. Okay, automatically for you. So that's kind of a cool thing about the x86. All right, and how does that work? Well, you have to put that stack in the right hardware register to start with so that the hardware knows what to do with when one of these occurs. Okay? And then the handler saves the other registers, does all the work, etc. Okay? So if you look through this, we save the kernel stack, we save the user stack, we save the user's program counter, we switch in the kernel stack, and then the kernel takes over as code's running and it does the rest. Okay, and then on return, we do the process in reverse. We basically raise the programming level from 0 to 3. We pop things off of the kernel stack, the E flags and CSEIP and the stack pointer, and we're good to go. And the user potentially gets to continue as if nothing happened. Okay, in the case of an interrupt, or in the case of an actual system call, then this process will return from the system call for us. Okay. Now I wanted to show you an example of that. So what's in gray here is kind of system mode, and this is our current situation where we've got the user stack. Down here we have the kernel thread stack, which is the TCB. Remember, that's how big is it? 4K, right? And notice that while the kernel or whether user code is busy running, we've got the instruction pointer is pointing at user code, the stack is pointing at the stack, and we're happy. And then all of a sudden a system call or an interrupt happens, and what happens next? Well, as a result of what I just showed you in hardware, now the instruction pointer is basically pointing into kernel code. The stack pointer is pointing at the stack. Okay, and we have also saved in the kernel stack these old pieces here, right? So we had a certain program counter and stack pointer that the user was using. We saved those on the kernel stack. Okay, and as a result of that transition. So take a look at that. So notice that as a result of the transition, we have got a new instruction pointer and stack pointer that's kernel based. We've saved the old stack pointer and instruction pointer. Okay, is everybody with me? So what's key about this is a couple of things, not the least of which is that the kernel stack is in place. So the kernel doesn't have to assume that the user hasn't screwed things up. Okay? And notice that the kernel is only using its own stack. Now, as we go forward, it also saves a bunch of other registers. Okay, so these are the remaining user registers get saved by the kernel. And so now at this point, we have saved enough stuff that we can go ahead and use the processor without risking what the user code was doing. Okay, and then we do some stuff, we're ready to resume. Okay, and then we're basically going to just undo what we just said there. And notice, by the way, while we're busy processing, we've messed up these registers. Okay, that's why they're red. I don't know, whatever the kernel was doing, it was fine. But now we're undoing this, so we restore the registers, and then we return to kernel mode, to user mode, and that does this last little restoring of the program counter and stack pointer, and now the user code gets to pick up where it left off. Yes?
At the moment the interrupt occurs, how do we get access to the kernel?
At the moment, so repeat your question. So,
So when the interrupt occurs, how do we get access to the kernel stack pointer so that we can
So at the point that this interrupt occurs, that kernel stack pointer comes from a register that you set up in advance, and so the hardware does all that switching for you. Okay, that's a good question. So if we go back to this previous slide here, that's actually part of the x86 spec. Okay, that it switches that kernel stack pointer for you. Okay? Now, in a processor that doesn't have this level of complexity, I'm going to say this is convenient for a class like this. This is not fabulous from a complexity standpoint. You would make sure that on transition in, the first thing that the code did in the very beginnings of the interrupt handler would be swapping the stacks. But you guys don't have to worry about that because it's being done by the hardware for you. Assuming that you've set up the stack pointer in advance by storing it in the right hardware register. Okay, and if you want to take a look again, there's tss.c and interstubs.s. Okay, now let me show you one other fun thing about this. So here we are. Okay, notice that this is exactly where we were before with a system call or an interrupt. And if instead of returning to the previously running user program, we return to something else, then what happens here is maybe we do a scheduling operation where we pick somebody else to run. And in that case, what we're going to do is now we're going to switch to a new TCB, a new kernel level stack. And that now has this set up so that when we go to restore, okay, we're actually going to restore a different user thread. And so that is exactly that. You know, an interrupt occurs, we switch into a new user, schedule a new user. Okay? And actually, I realized there's a bug on this slide. I should have these two guys were on the stack there too. Okay, and so basically there's a bunch of these TCBs that are sitting inside the kernel that are the kernel thread halves of user threads, and so we can just, by switching to which one is currently active, that basically gives us the ability to switch into a new thread. And I don't know if you noticed here, but the page table base register has got a prime on it, so we changed the page table, and we also changed the stack pointer, okay, so that it's pointing at a new TCB, which is the one we're switching to. Okay, good? All right. So let's talk about ThreadFork a little more. So this is all fine and dandy, but how do we actually get started? Okay, and so ThreadFork is a user-level procedure that creates new thread. Arguments to ThreadFork are a pointer to the application routine you want to run, okay, and a pointer to an array of arguments, and maybe a size of the stack to allocate. And the implementation is basically you got to sanity check things. You enter kernel mode and sanity check again. You allocate the new stack and TCB. You initialize the TCB and place it on the ready list. And then poof, it runs. Now, of course, you may not believe that, so let's go a little further into this. So how do we initialize the TCB and stack? So if you think about it, what we really want is we want a new kernel thread or a kernel stack and a new user stack in order to set up something to run. Okay, because we're trying to make a brand new procedure run from scratch. And so basically what we're going to do here is we're going to take something we call a ThreadRoot stub, and we're going to stick it into a kernel thread and then just put that thread onto the schedulable, runnable queue. Okay, do we have to initialize the stack data? Not much, no. Okay. So let's take a look. Let's see, did I leave an extra slide? I did leave an extra one in there. So how does the thread get started? Well, notice that what we're going to do here is we're going to try to allocate something on the side such that when we execute switch, it's going to switch over to this new thread. Now notice that the new thread A doesn't exist yet, doesn't have any stack state, doesn't basically have anything. So how can we fake something out so that it'll just start? And that's what we're going to do here. We're going to allocate a new TCB for this guy, and we're going to set up its stack pointer to be pointing at the new stack, and its return PC to be pointing at the ThreadRoot. And we're going to put some arguments in a place where ThreadRoot can find them. And then we can't really call switch without starting the thread. So we set up to point at the thread, put the other things on the stack, okay, and eventually run new thread will select this PCB and or this TCB and run. And so really what's happening there is when it's selected, it returns and immediately starts executing ThreadRoot. And then ThreadRoot looks like this. Okay, it's going to do some startup housekeeping. It's going to switch to user mode, and then it's going to call our function, and then it's going to execute finish. Okay, and so startup housekeeping has some things like what's the start of the thread. And so this is what ThreadRoot looks like. It basically starts stack growth downward. It's running in kernel mode for a brief little period of time. It starts running the function, and then we pick up from there, and we're now running as a full-blown process, or full-blown thread, excuse me. Okay, and then when we finally return back into ThreadRoot, the very last thing that happens is it executes thread finish, which cleans up the thread. Question? Yes? So there is a question of how do you pass into ThreadRoot these two arguments. Is that what you're asking? Yeah, so it depends on which processor you have. Okay, so if you have a RISC processor like RISC-V, of course arguments are in registers. Yeah, here? Well, by calling, this is the frame that starts by calling. So by executing ThreadRoot here, right here when it calls this function pointer, that's the point at which this gets put on the stack. So this is the result of actually executing ThreadRoot, that we have this stack frame set up. I'm not sure that I've answered your question yet. Okay? So, but back to the question, the other question, which maybe you weren't asking. So you might ask the question, where did these two things, how did they get reflected to ThreadRoot? And the answer is in a RISC processor, they would be in registers. In the x86, they might have to have been pushed onto the stack. Okay. All right. So Administrivia, so today's group creation deadline's tonight. Okay, 4 folks per group. And, if you sign up with less, you may end up with an extra partner, because we're trying to make all our groups have 4 people in them. All members of your group need to have the same TA, so you need to figure out whether there is a section that you can all attend. Okay, figure out whether there's a time slot you can all attend. That's important. Okay? Now, in the worst case, and only with special talking to us, it's possible that members of your group might be split across different sections with the same TA, but that's like a special case. Okay, and let me explain why. The reason is that your TA is your gateway into this class. They're the ones that know you. Okay, and you want to make sure you know your TA really well, because then they'll know how well you participated and what you've done. And also in the case of group projects, they get a better idea of who did what in the groups. So it's very important that we pick a TA that you guys can all be part of. So that's why we want you to all be in the same section. And section attendance is definitely mandatory in this class. So, okay. Questions? All right. So Right now we're basically talking about kernel-supported threads, where every thread has a thread control block, and in that thread control block it sort of keeps track of which process it's part of. And the OS scheduler is actually scheduling TCBs, not PCBs. Okay? So that makes sense, right? Because the thread control blocks are, the threads are the units of concurrency and computation, not the process, which is the unit of protection. All right. And so actually you can take a look at this previous diagram we had, and rather than process, we have thread, runs for a little while, and then we save stuff into TCB 0 to 1, whatever, and then we run in thread T1 for a while, and then we reload the state and continue. Okay. Yes? You mean here? Yeah. Well, every process control, so there are one or more threads per process. Good? Yeah. Okay, great. Okay. So just to pop up a level here for a moment, there are user-level multithreading that you too can do in your spare time. So there are, for instance, pthread create. So pthreads is, P is for POSIX threads. Okay, that's a standardized thread mechanism. So pthread create will create a thread. Pthread exit will end the thread. And pthread join says, suspend me until the thread that I'm giving you an argument exits and then wake me up. So that's a join pattern. Okay. And so here's a fun example, perhaps. And if you look here, we basically have in our main, we sort of say how many threads there are, whatever. But what happens is we allocate an array for the threads, and then we go through, and for each thread, what we do is we do a pthread create, and we put the thread in the array of threads, and the function thread fung right here is this guy. Okay, and that's one that's going to say thread X, stack, whatever, and so on. And then after we've started all the threads, and by the way, the guy in the main here is the parent. We start all the threads, and then what this at the end does is it goes through each one of the threads, and it says pthread join on that thread 0 through n. And we know that when we've exited this for loop, we've joined with everybody, so all of the child threads are done, and we can exit. Okay? All right. And so here's an example of this running, and as it's printing out, it says, thread 1, thread 3, thread 2, thread 0. Notice that the ordering is a little scrambled, and that's because the scheduler is scheduling them when it does. All right? Good. How do you tell if something's done? Well, you may have to have some sort of join operation. And notice, by the way, so this pthread exit invokes the corresponding join. Is that clear to everybody? So when you say join, the person who called join goes to sleep until the corresponding exit happens in the child, and then it wakes up. Okay. Good. So this is really a fork join pattern. Main thread creates a collection of subthreads, passing them arguments to work on, joins with them, collecting the results. Okay, and this is a very common pattern which you're going to run into a lot. Okay. So this thread abstraction, let's go down this path a little bit here. This thread abstraction is sort of an illusion of an infinite number of processors, because I can just keep creating threads, right? The problem with that illusion is it's not actually real, right? It's an illusion. And so if you go a little too far with that, you'll notice very rapidly. So what happens is too many threads yield to nobody making any progress. Okay, you get a type of thrashing going on. And so the physical reality here is that only a small number of threads can actually run at the same time, depending on how many cores there are, and the rest of them are sleeping. Or they're not really sleeping. They're on the ready queue, but they're not running. Okay. And the programmer view is that you have, say, these instructions, x equal x plus 1, y equal y plus x, whatever. one possible execution is that these things run like that. Another one is that x equal x plus 1 runs, and then we've got a long suspension while the other things run, and then y equal y plus x, and z equals x plus 5y. And another possibility is like this. So, once you have a lot of threads, chaos ensues, right? Because you don't know when the scheduler is going to mess you up. Okay, and I like to think of the scheduler as a malicious entity whose job it is to screw up your program as best it can by deciding when to switch. Okay? And so, as we go forward in this class, we're going to have to start figuring out how to design things correctly by construction so that they survive all possible interleavings without getting an incorrect result. Okay? So this is going to be designed for correctness. And on the face of it, this doesn't look so bad. It's like, yeah, so you're delayed for a little while. Well, the problem is that if some other thread thought that all three of these things were going to happen atomically together, and instead they don't, then these threads in the middle could get some really weird results. Okay, and that could be a big problem. You know, so possible executions throws thread 1, thread 2, thread 3, or they might run all parallel, or they might run in some weird combination. Okay, all of these things are possible. This guy here, this is only going to really happen if you got multiple cores going on, so you can have real parallelism. But real parallelism and some weird interleaving, they sort of all have the same concurrency issues with them, and that you got to make sure you got locking working properly. There's the word locking again, right? Okay, so let's push on this thread a little bit further. So we've talked about this thread control block. The thread control block in Pintos is a 4K block that's got space for storing all of the saved registers, program counter, pointer to stack. It's got all the scheduling info, pointers to the PCB, etc. And the OS keeps track of TCBs in kernel memory. So now, probably not today, but we'll talk about a user-level threading possibility where the thread scheduling is being done at user level rather than in the kernel. But for today, we're talking about kernel-level thread scheduling, okay, which is basically the kernel is keeping track of all of these things, and the kernel is making scheduling decisions. Okay, and so basically a multi-threaded process looks like this, where one PCB has many TCBs. All right. Now, of course, Pintos has only one thread per process. Okay, so that's a little bit simpler. Okay, so switching threads within a block is a simple thread switch. Between blocks requires changes to memories and I/O address tables and everything. Okay, so there is some cost to switching from one process to another because you got to switch out the address space and you got to switch a bunch of things. Switching between threads in a process is simpler. Now, remember some definitions which yes? Well, if you have more than one thread. Because the TCB has a stack. It has the kernel thread stack and space for the registers to be saved. And so every thread has to have a separate one of those. So that's unique state for execution. Okay. So here's some terms. So multiprocessing is multiple CPUs, multiprogramming, multiple jobs or processes. Multithreading, multiple threads per process. I'm sure you've heard all of these terms one time or another. What does it mean to run two threads concurrently? It's basically that the scheduler is free to run them in any order and interleaving, FIFO, random, etc. The dispatcher can choose to run each thread to completion or time slice in big chunks or small chunks. So multiprocessing, here we see that multiple things are actually running at exactly the same time. So that requires multiple cores, for instance. Multiprogramming, what you see here is we have A, B, and C, but we have many interleavings. We have the A, the top one, basically you run A to completion, B to completion, C to completion, and the bottom one, you're interleaving them in any arbitrary way. Okay? And so just to, not to put too fine a point on it, and just to say this again, it's very important to make sure that when you write your programs that are going to operate in the presence of more than one thread, that they're correct under all possible interleavings. And you can't test for that. Actually, that's not quite true. You can test for some interleaving issues, and there's been a lot of work on that, but by and large, most of the things you could get into, you can't really test for it. And so that leaves design for correctness, okay? There have been some progress on testing for some of these things, but let's just assume for a moment you can't test for this. So if a dispatcher could schedule the threads in any way, then programs must work under all circumstances. Can you test for this? No. How can you know if your program works? Well, one thing is if the threads are really independent and they're not sharing any information, there's no state shared, they become deterministic because the input state determines the results and it doesn't matter what the interleaving is. So if they're not sharing any information and they're just interleaving, at worst that's a timing change. And assuming that the correctness of your task doesn't depend on timing, then if the threads are truly independent, then you're not going to have to worry about it. Okay? It becomes reproducible. Scheduling doesn't matter. If they're cooperating and sharing information, okay, now we got a problem, okay? They're non-deterministic, non-reproducible. Non-deterministic and non-reproducible means that bugs can be intermittent. This is what we call Heisenbugs, okay? And you will definitely run into Heisenbugs as you go forward if you're not careful. These are the bugs where you attempt to find them, you attempt to put in printfs to find them, and they go away. Okay. Yeah. So this is why you just got to be really careful how you write your code, right? So interactions complicate debugging. So is any program truly independent? Well, every process shares the file system, OS resources, network. An extreme example is that a buggy device driver maybe causes thread A to crash and causes thread A to crash independent thread B because they're using the same underlying system. So even if the threads are independent, as far as you're concerned, they're not independent because they're running on top of the same operating system, right? So here's an interesting example. Where you don't realize how much you might depend on reproducibility. Suppose that there's evil C compiler modifies files behind your back by inserting errors into the C program unless you insert debugging code. Or another, non-deterministic error is really hard to find. Memory layout of kernel and user programs depends on scheduling, which depends on timer, etc. And original Unix had a bunch of non-deterministic errors like this. Something which does interesting I/O actually is a positive here. How many of you have generated a long cryptographic key by typing a bunch of, typing on a keyboard to get enough randomness to put in there, right? So there's an example of non-determinism actually being used for a helpful thing. Okay, so why allow cooperating threads? Well, people cooperate. Computers help and enhance people's lives, and, people are non-deterministic. So there are many advantages to sharing resources, which is why we don't just throw it out of hand. So sharing of resources, one computer, many users. One bank balance, many ATMs. Speed-ups might be an advantage, right? Overlap I/O and computation. Many different file systems, do read-ahead, etc. Okay, or modularity. So, for instance, you could chop a large program into multiple pieces. So did you know that the C compiler that you all use does the following? It basically runs the C preprocessor piped into the first phase, piped into the second phase, piped into the assembler, piped into the loader. So it's actually been separated into separate processes that then feed into each other, and that's how it works. Okay? And so that makes the system easier to extend. So there's another example where cooperating threads can be useful. Okay, so let's take a brief break and come back and we'll continue with what we're doing here. I can figure out why my animation is broken. Great. Let's continue. So let's take an example of a web server here that's a common thing that we talk about in this class. So for instance, how might this actually work where we have one server, many people talking to the server? So a non-cooperating version might do the following. So there's a loop in the server, and what it does is it accepts a connection, and then it makes a brand new process or through fork to service that web page. Okay, and it just keeps doing this over and over again. So now what's happening is that for every incoming query, we make a brand new process. Now, certainly that's secure, I guess. Okay, because you got a brand new process regardless of what's going on. The problem is, of course, that creating a process is potentially quite expensive, especially if you've got something that's very popular. You've got a slash dot effect going on. So we might want to do something a little bit different, like use threads for it. So let's use a single process, multiple threads. And so now we really haven't changed anything, it looks like here, right? We grab the connection and then we do a thread fork instead. Okay. So looks almost the same, but has many advantages. So now the different threads can all share the same file caches in memory. Results of CGI scripts, etc., can be shared across threads. So that seems good. Okay, so threads are much cheaper to create than processes. So this has a lower per request overhead. And we'll answer that question later. What about denial of service attacks? Okay, it seems like this particular situation here is still a little bit challenging. If all of a sudden 1 million entities all tried to query the web server at the same time, we're going to get 1 million threads. Even that's going to slow the system down. In fact, it might cause a serious problem. So instead, we need to limit the parallelism that we allow. Okay, we're not going to let it get out of hand. And so now we're going to do something called a thread pool. Okay, so the problem with the previous version is unbounded threads. When the website becomes too popular, the throughput basically sinks through the floor. And instead, we allocate a pool of worker threads like this. So now when a request comes in, it gets picked up by the master thread, which then enqueues it. And then this is this little pool of threads. Okay, and what happens is only a finite number of threads are active. And so all of the other queries, in the case of a slash dot experience, are all queued. They're not threaded. They're not running. Okay, and so we only have a small number of things running at the same time. And so what this looks like is the master allocates a fixed number of threads, and then it says, well, true. It accepts a connection and queues it and wakes up the queue. And it keeps doing this over and over again. And all the master is doing is it's sort of acting as a gateway into the queue. But the queue is just in memory, so maybe that's not as big a deal as having a bunch of threads running. What does each worker thread do? Well, it says, well, true. It tries to dequeue from the queue. And by the way, that dequeue operation will put that thread to sleep if there's nothing ready to run. And we'll talk about how to make that work in a little bit. If there's nothing there, we go to sleep. Otherwise, we service the web page. So basically what we've done here is we've restricted the parallelism to a fixed amount, and as a result, sort of avoided having too much parallelism going on at once, and thereby controlled the system resources that are in use. Okay? Questions? Yes? Well, it'll cause a lot of latency, but the server won't crash. So I guess that's causing latency versus causing a lot of latency. 6 of one, half a dozen of the other, I guess. So here's the, let's dive into this problem a little bit more here of synchronization. So here's an ATM situation where you have the central bank has a bunch of servers, and then you have a bunch of ATMs out here. And we want to serve a set of requests and do it without corrupting the database, and don't hand out too much money, because then the bank isn't staying in business very well. Suppose we wanted to implement a server process to handle requests. So we could do this. Well, true, receive request, process request. And we do this over and over again. This is fine, except it seems doesn't have much parallelism, right? It doesn't have any parallelism. And what does process request do? It says, well, if it's a deposit, do this. If it's that, do this, so on and so forth. Deposit says, get account for the account ID, update the balance, store the result back into the account, etc. So this may use disk I/O here. This involves disk I/O for sure. So the question is, how do we speed this up? Well, we would like to have more than one operation actually happening at once, so that more than one customer can be served at once. Okay? Because if there's a lot of customers, they're all going to get serialized at this loop, okay, which would be kind of bad. Now, there are many ways of doing this, and we'll look at a couple of them. But the moment we start opening this up to having more than one thing happening at once, we're suddenly going to have concurrent threads, and now things are going to get broken pretty quickly. So, for instance, suppose we only had one CPU. Okay, still want to overlap I/O with computation. Without threads, we'd have to rewrite in an event-driven style. Okay, so let's look at this. I want to just give you this example here to tease your mind with it a little bit. The idea is that we take our bigger, more complex task, and we split it into a series of events that are guaranteed to be short. Okay, and what happens is we wait for the next event. We say if the event is a request, We start the request. Otherwise, if the event is the account is available, continue the request. Otherwise, if the event is the account is stored, finish the request. So if you look back at this original thing, notice that in this process here, the places where we may be really slow are, for instance, here while we're waiting to get the account, and here while we're waiting to store the account value back. And so what I've done to do this as an event-driven style is I've identified those points as places where an event starts or stops. And so, for instance, when I get the ATM request, I start the request, and then I end my event, and I go on to the next one. And so I can have multiple people for which I'm doing such an event at once. Okay? And so this is a way of basically scheduling a bunch of things simultaneously. Okay? And what if we missed a blocking I/O step? Well, suddenly we're in trouble because this isn't really overlapping things very well. What if we have to split codes into hundreds of pieces, which could be blocking? So this event-driven style is sort of an alternative to threads. But as you can see, it could get very tricky to try to split things up into enough little pieces. Now, before you reject this out of hand, I want to say that there is a type of code where this event-driven style is used a lot. Does anybody know what that is? Gaming loops, yes. Anything in, less specific than gaming loops, but yes. Yeah. Yeah, well, windowing systems, okay? So windowing systems tend to use this kind of loop where mouse events and draw events and all that sort of stuff on the screen, they're all handled in a big loop like this, okay? So everything, key press events and so on. So a lot of the user interface things are designed this way. But let's go back to a lot of graphical programming. So can threads make this easier? Well, we might think so. One thread per request. We just do the following. We sort of say, well, we have our deposit, and we have multiple threads, so each incoming request gets a thread. We're good to go. No problem, right? We have multiple things running at the same time. Everything's faster. It's great. Oh, wait, it's not great. Because look what happens here. This gets subtle quickly, right? Suppose we have two threads, and they're both working on the same account, okay? Because you're depositing $10 into your account, and your parents are depositing $20,000. Oh, wait, does that ever happen? Okay, $20,000 into your account. Notice what happens here. Thread 1 gets the balance, and then thread 2 swaps in, loads the balance, adds an amount, stores it back, and then thread 1 returns, adds an amount, stores it back. What happens at the end of this? Yes? Yep, thread 2 is completely erased from existence, right? None of what it did gets registered. Okay, so this is an unfortunate concurrency bug. Okay, and it's an example of what happens when you have multiple threads running at once. What you really need is you need somehow to have this whole chunk atomically executed so that it can't get split up. Okay, because otherwise you're going to get incorrect results. All right. And by the way, you run into similar problems with the event-driven too if you're not careful. So this is a generic problem. So the problem is at the lowest level here. Most of the times, threads are working on separate data, so scheduling doesn't matter. Thread A, x equal 1. Thread B, y equals 2. Doesn't matter. However, what about this? Suppose y is 12. So thread A does x equal 1, x equal y plus 1. Thread B does y equals 2, y equals y times 2. What are the possible values for x? Let's just suppose that this is something, RISC processor, something simple. What are the possible, yeah? Okay, so if we see here, if thread A runs all the way through, x could be 13, right? If we get x equal 1 and we update y equals 2, then we could get 3, right? Or y equals 4, we get 5, right? So there's several options here depending on interleavings. Yep. Okay. Or what are the possible values of X here? You guys are all saying, okay, so 1 or 2, what else am I missing, right? Yeah, it could be 1 or 2. Just seeing if you're still awake. I suppose for a serial processor, it could be 3 if it's interleaving the bits. Now, fortunately for you guys, we're not dealing with bit-level interleavings, but you got to be careful here, okay? So, to understand a concurrent program, we need to know the underlying indivisible operations. And so an atomic operation is an operation that always runs to completion or not at all. So it's indivisible, can't be stopped in the middle, and state cannot be modified by something else in the middle. It's a fundamental building block. If no atomic operations, then there's no way for threads to work together, unfortunately. On most machines, memory references and assignments of words are atomic. So consequently, the weird example that produces 3 can't happen. Many instructions are non-atomic, so double precision floating point store is often non-atomic. Okay? VAX and IBM 360 had an instruction to copy a whole array. That wasn't atomic. Okay? So here's another example. 2 threads, A and B, compete with each other. One tries to increment a counter. The other tries to decrement the counter. Now, if you remember, when I talked about fork, I had a fork version of this, right? Where I had I at the beginning and we forked. There was no complexity there because the I's were different. Here, the I's are not different. Okay? They're running together. So the question is, who wins? Assume that memory loads and stores are atomic, but incrementing and decrementing are not. Who wins? Could be either. Is it guaranteed that somebody wins? Not clear, right? What if both threads have their own CPU running at the same speed? Is it guaranteed that it goes on forever? Well, the sun could explode. That's true. The problem is there really is no, cache misses could cause enough non-determinism to change the result here. Okay, so this is just bad. This is bad coding. So here's a hand simulation. Thread A, thread B. Okay, thread A loads the value. Thread B loads the value. Thread A increments. Thread B subtracts. Thread A stores. Thread B stores. So now we've gone -1 here at this point, right? And we're off. A gets off to an early start. B says, I'll go fast, and tries really hard. A goes ahead and writes 1. B goes ahead and writes -1. A says, huh? I could have sworn I put a 1 there. Can this happen on a uniprocessor? Yes. With hyperthreads, definitely. But unlikely depending on the quantum of scheduling. Okay? So, but this is an example of something you just don't want to have to depend on or reject. Bottom line, this is just a bad program. It's just, you can't figure out why it works the way it does or whether it should work this way. Okay? Because it isn't working. So the correctness requirements are important here. So threaded programs must work for all interleavings of thread instruction sequences, cooperating threads inherently non-deterministic and non-reproducible, really hard to debug unless carefully designed. I wanted to tell you briefly about the Therac 25, which was a machine for radiation therapy. Once upon a time, software control of electron accelerator and electron beam X-ray production, software control of dosage. Okay? And software errors basically caused the death of several patients. And these were concurrency errors. Okay, so what happened was, because of the way the software was written, when people who were really good, so when the nurses who really knew what they were doing went in there and were trying to quickly enter the data, the fact that they were entering it too quickly caused the system to screw up, and it would misposition the target, and as a result, the patients would get an overdose. Okay? So a series of race conditions and shared variables and poor software design basically ended up with some pretty serious flaws and death. Okay? Here's a quote from something. I actually usually put this up. I'll make sure that you guys can read this if you want. But they determined that data entry speed during editing was the key factor in producing the error condition. If the prescription data was edited at a fast pace, the overdose occurred. So precisely the people who were confident enough in how to use this system were the ones that were causing the problems because they were working too confidently and rapidly. So this is a good example of why to be very careful with your concurrency bugs. Okay, so I want to get a motivating example here. This is the too much milk example. So the great thing about operating systems is there's all sorts of analogies between OSs and real-life problems. Helps you understand real-life problems better. So here we go. You and your roommate have a deal. Whenever anybody discovers that the milk is gone, they go buy some more, right? So time 3 o'clock, person A looks in the fridge, they're out of milk. They leave for the store. Meanwhile, person B looks in the fridge, you're out of milk. They leave for the store. Person A buys some milk. Person A arrives home, puts the milk away. Person B arrives at the store, etc., etc. And we have too much milk. Okay, and the second person could have bought ice cream or something. It would have been a better idea, right? So, synchronization is using atomic operations to ensure the cooperation between threads. For now, only loads and stores are atomic, and we're going to have to show that it's really hard to build anything useful with only reads and writes. And I'll tell you about this next time when we pick this up. Mutual exclusion is ensuring that only one thread does a particular thing at a particular time. One thread excludes the others while doing its task. So we need mutual exclusion here because what we need is we need to make sure that only one roommate can actually be out buying milk at a time. Okay, and that so we're going to have to redesign this algorithm using mutual exclusion somehow. A critical section is a piece of code that only one thread can execute at once. Okay, only in one thread at a time. We'll get into this section of code. The critical section is the result of mutual exclusion. The critical section and mutual exclusion are two ways of describing the same thing. So a lock prevents someone from doing something. So the idea here is very simple. You lock before entering the critical section and before accessing shared data. You unlock when leaving and after accessing the shared data. And you wait if it's locked. So the important idea here is that all synchronization involves waiting. So the way you prevent these weird problems that I've been telling you about is you wait. Somebody waits. One of the threads waits until the other one is done enough to be atomic, and then it gets to go. Okay, so pretty much every synchronization problem that you'll ever encounter is solved with a proper amount of waiting. And that proper amount of waiting gets put in there by using the proper locking mechanisms. Okay? So, for example, the way you fix the milk problem is by putting a key on the refrigerator. Okay? You lock it, and you take the key if you're going to buy milk. Okay? Maybe that fixes a little too much, right? Of course, we don't really know how to make a lock yet. Okay? So the correctness properties are you need to be careful about correctness of concurrent programs since they're non-deterministic. The impulse is to start coding first, and then when it doesn't work, pull your hair out. Okay? Not a good idea. So instead, you want to think first, code second. Okay? Always write down the behavior first. So what are the correctness properties of the too much milk? Never more than one person buys. Somebody buys. Okay? Those are the two key things, right? Never have more than one person buy, and somebody always buys. And we restrict ourselves to using only atomic load and store operations as building blocks. And we're going to do this solution. I'll show you this first solution very quickly. We'll pick this up next time. But you use a note to avoid buying too much milk. You leave a note that says, it's kind of a lock, I'm buying, and you remove the note after buying, and you don't buy if there's a note. Okay? So here it is. Suppose the computer tries this. If no milk, if no note, leave the note, buy milk, remove note. Does this work? Well, if you look carefully, what you'll find is it doesn't. You can still get multiple people buying them. All right, we'll pick this up next time. So, in conclusion, hold on. Concurrent threads, very useful as abstraction, right? Allow transparent overlapping of computation in I/O and parallel processing when necessary. But they introduce all sorts of problems with shared data. Programs must somehow be insensitive to scheduling changes. And so we're going to show how using atomic operations of various sorts, of which locking is going to be the first one we talk about, will help solve this problem. All right. Ciao. We'll see you on Thursday.
Hi.
Hi.
We've been waiting for several hours to ask you this question. Yeah. Okay. So we were working earlier on the project, and we were taking inspiration from like the red and blue slides about like switching threads.
Uh-huh.
We're quite confused what happens when there's no thread. There's no second thread. So, like in the slides,
you have thread S.
Yeah. So like we're pretty confused about like what like the thread root stub is supposed to represent.
You like what I'm saying on the thread? You mean what I was saying on one of my slide?
It's like chalk. I can draw it. Yeah.
Hey, you want to just use this?
What you're talking about my slide?
We're just confused in general, like what happens. Yeah. So
You might want to be a little bit careful about getting too close to me because I might be mildly contagious.
okay.